Hi everyone, welcome to a lecture on accessing files in the C programming language. As we've mentioned before, everything in Unix can be looked at as a file. Everything except processes, that is, but for the most part you can look at things as files. So the contents of a directory might include things like hard links, symbolic links, the named pipes, which we'll talk about coming up here, some device character special files. The block special files are things like drivers, things like that, CD devices that have been attached, and then some named sockets, which is a networking methodology that we'll get to. From the perspective of a system programmer, these files are streams of bytes, and they could all just be accessed as an array. Even new lines and carriage returns, all that white space, they're all just bytes that are contiguously connected in these arrays, in these streams of data. And a file is something that's persistent. So that doesn't mean that it lives forever, but at the very least it's something that's going to be there the next time you need to go back and look at it. So how do we access these files for reading and writing? So opening a file is going to be opened in one of three different modes, either as read-only, write-only, or reading and writing. All three are possible. When you open a file for writing, there's a bunch of questions that come up. Should you delete an existing file that has the same name? If not, if it's already there, where do you want to start writing into this new file, or reading for that case? Do we start writing at the beginning of it? Do we start writing at the end of it, somewhere in the middle? If the file doesn't exist, does that necessarily mean that we have to create it? And if we do create it, what are the initial access permissions that that particular file should have? So the file pointer is going to be the location of where the next file operation will occur in that open file. So the default start position for a file pointer is at position 0 for that file. And we're going to maintain a separate file pointer for every separate file that we open. So each open file gets its own file pointer. And all the operations that we're talking about, reading and writing, both of those have an effect on the location of this file pointer. And they will each move the file pointer as those commands are run. So here we start at 0 and we have a file that has a bunch of data in it. So looking at at some code for a read example here, so we include some necessary header files and we launch into our main function here. And here we're defining a string as what's holding a file path here, complete with a directory inside. We will declare a file descriptor as an integer, and a file descriptor is a handle, basically, a reference for the given file that we're working with. We use the open function and pass in the path to that file, and then the permissions, or the mode that we want to open this particular file in. And then our file descriptor return value is either going to be a valid file descriptor, or if it's less than 0, then it means there was some horrible problem, and we have to take a look at it to see what the problem is. And here you can see I'm exiting out when we have a failed open call. At the end, we close off the file descriptor and then return. Note that file descriptors will be closed once your program shuts down, but it's good practice to get in the habit of closing them down yourself. You may have used fopen and fclose. Those are for file streams, and we'll talk a little bit more about those coming up. So open for writing, on the other hand, is extremely similar, with the primary difference being here we're going to change out the flag here. So here we're opening it for writing only. And for the most part, everything else is going to be the same. We indicate what's happening to the user, and here I'm going to use this perror function, which prints out an error relative to some variables that are being tracked in terms of what the actual error is. And in this case, this perror function is going to say, I've got an error that's happening in main, and then exit out. So when we open a file for writing, so one of the questions is, do we delete all the contents of an existing file that has the same name, or do we just write over the existing contents, leaving it there? One of the flags that you can add in is the trunk flag for truncate. So as an example, when we open up a file, we can open it up for writing only, and we can bitwise OR this trunk flag, and the joint combination of these two flags, when the file is opened, if it finds one, it will delete all the data that's in it and set the file pointer to position 0 so that we can start writing right from the beginning of that. This is handy if there's a new log file that you want to have opened every time you fire up your program, so you can always know that whatever the contents are that are in there, it's fresh. If we want to append, on the other hand, to the end of a file, we would instead pass in the append flag, o_append. Before every write, then the file pointer is going to be automatically set to the end of the file for this particular file. So the example, when we open, here is write only bitwise ORed with the append flag. So that opens it up in append mode. Let's take a look at some kind of graphical examples of what's happening here. So if we have a file that consists of what looks like the first line of a shell script, then we use the append flag. Then it means that the first character that any subsequent read or write command is going to be pointing at is the one at the end, or just past the end of the file. So if we read from this, there's either nothing there or junk or something irrelevant. We wouldn't want to read from there. Or if we write to it, we know that we're writing to a space that is not filled with data from the file. So to open a file that doesn't exist, there's a couple of things that we have to do here. So first of all, we would use the create flag. And what that will do is it will specifically create one if it's not there. And the other thing that we have to do, our third parameter, is you have to pass in the permissions for the file. Now, you do have to do that, and that happens whenever you're using create or temp file. But if you don't include it, then C will fail in bizarre, silent ways. So it may not let you know that this opening method here is incorrect, but it will definitely do strange things with that file. You definitely need to add it there. And just to help reinforce the thought, again, the third parameter of open must be used when you're creating a new file, when you've requested that a new file be created. And these are the same octal permissions bits that we've seen before with the change mode command. So for example, 0600 would be for just the owner of that particular file, give him read and write access. You can also use some flags that you can bitwise OR together that are a little more human readable. So for the user, give us read permissions and write permissions. So both of these are going to be the same. So either 0600 or you can bitwise OR the same flags. So just depends on which one you want to do. lseek is a C function that allows you to manipulate where that file pointer is. So when we want to control how we're getting into those bytes and those bits, we can mess around with the file pointer directly. So here's an example. We can move directly to byte 16 in the file by calling lseek and giving it the file descriptor that we want to mess around with, giving it the new position and using the seek set flag. That says set yourself to position 16. So if we want to move forward 4 bytes, then we can say seek from your current position forward 4. Then we can move to 8 bytes from the end by saying from the end, seek end, move backwards 8 bytes. So we can control where that file pointer is. Alright, so a little graphical example here. If my original position was here at this slash, and I want to seek set at position 9, then it doesn't matter where we were before. The seek set is going to set us to this position 9 here. Now note that this is 0 indexed, so this is spigot 10. This is index 10, bucket 10 in this particular array. Alright, so here is seeking from our current back 5. We use the seek cur flag and we go back 5. 1, 2, 3, 4, 5. And here we are at position with index 4, which is the 5th position. Here is moving forwards. So we'll start at position 4. We will seek from our current position forward 3. 1, 2, 3, right? Pointing at the B there. Here is seeking relative to the end. So we can say seek end, and we can say -3 from the end. So if this is our particular end cell, the particular end byte in our file, then we can go back 1, 2, 3. And we can also just seek directly to the end by using 0 seek end. That takes us to the same thing here, assuming 99 bytes in this particular file. And again, with seek end, it doesn't really matter where we started. We're referencing it based off of the end position. So if you've opened a file for both reading and writing, one thing that's interesting is that both of these operations changes the file pointer location. So the pointer is going to be incremented by exactly the number of bytes that are read or written. I will do some more examples of that in some upcoming lectures. So let's do a little quick read example. If our original position is at 0, and we are saying we run this C command called read, and we're saying, all right, read from the file pointed at by the particular file descriptor, and we are going to place the data that we extract from that file into buffer, and I want you to read 10 bytes. So starting at position 0, we're going to read off 10 bytes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It gets us all the way out to the S. And then the pointer points at the next byte. And you can see that fills our buffer up with everything but the H. Write does the same kind of thing. Note how they're both moving the pointer around. So if I start at byte 7 here, index 7, and I write forward 4 bytes, and my buffer contains TCSH, that's what's in buffer, we're going to write this into the file descriptor. So now I can replace this with TCSH, and note that the file pointer is 1 more ahead of that when we finish. So let's do a complete read and write example here. So all the necessary headers are included, and we start out with a file descriptor, an integer that we'll leave uninitialized because we'll set it with an open command. We have 2 different strings, different C style strings that we're going to allocate. One is a path to a new file, and one is just a string. We're going to use a special type that's reserved for C and Unix that we can use to track the number of bytes that are read and the number of bytes that are written. And then we have a buffer, a character array here, which is called read buffer, and we'll just allocate that for 32 bytes. Then here's our open call. Here's the path that we previously specified as new file.txt. Here are the mode bits. So open it for read write, create it if it doesn't exist. If it does, truncate it. And then since we used the create flag, we have to use the permissions bits. So here we're saying open it up for reading and writing, which matches with the mode bit that we gave over here. If these things don't match up, if they don't work together, you can get really strange errors where writing to the files doesn't work, or you get errors when you write to the files even though it compiles just fine. Then we test our file descriptor to make sure it gave us a real answer here, or a successful open call. And if it failed, go ahead and indicate to the user how it failed and then exit the program. Alright, so here we're going to try writing to that file. So I run the write function, and I pass in the file descriptor for the file that we've opened up, pass in the string that we intend to write, which is given, and it contains the business. And then we're going to say how many bytes we intend to write. And that is string length of given, so how many bytes are in given, times the size of a character, because this field here is the number of bytes, not the number of characters. That's a subtle difference, but it's important. Even though it's a tautology to say how many bytes is a character, this always returns 1, it's still important to realize that we're talking about bytes here and not characters. Then, once that has been done, and we've written that data to the file, we're going to use a memset here. And what memset does is it'll set that array to whatever we indicate here. So we're saying take read buffer, which we never initialized properly, right? Who knows what's inside this thing? So take read buffer and set everything in it up to the size of read buffer, so the entire thing, set all of those to null terminators. Basically cleans the whole thing out. So when we put a string into there, no matter where the string ends, we can be guaranteed that the character after the end of our string is going to have a null terminator. And without doing that, you can get some really strange errors. Like you try to print out that particular buffer, and because it has no null terminator at the end of it, even though you've written data into it, you won't be able. It'll just print what you what you pass into it, plus everything else that happens to be in memory until it hits a null terminator. And by the same token, we're going to lseek to the beginning of the file. So note that we're going to be reading and writing to the same file. So since I want to read back what I wrote, I need to lseek back to the front. So I seek set back to position 0. And then we read. So here's our read command, and we'll read from the file descriptor into our read buffer. And then we are going to read in size of read buffer bytes. So grab the read buffer and do it for read buffer bytes, and that's worth 32 bytes because 1 byte per character gives us 32, so pass in 32 bytes. And note that for both read and write, we're tracking the number of bytes that were read and written, and we can compare that to what we asked it to do, and if they're the same, we know everything's good. If it didn't succeed, then we know something went wrong. And then just print it out. So print out the file contents. There's our %s to say a string, and then push through the read buffer into it and exit the program. So note, these are really important steps to avoid some nasty bugs when you're reusing the same file for reading and writing, and for clearing out arrays before you use them. Okay, so the standard I/O library in C. This includes a lot of different functions that we frequently use, but we haven't really used so much so far in this lecture. So that would be things like fopen and fclose, the fprintf versions of printf, the sprint, so string printing of f in a formatted manner, a bunch of different functions that are fantastic. And these functions are going to do things like automatically buffer the input, automatically buffer the output, and do all that for us behind the scenes. They're very easy to work with in line mode, so just read one line at a time, write one line at a time automatically. They work great. A lot of powerful formatting tools for strings and numbers, which we've seen before, and they all live in that standard I/O header file. So if they're so amazing, then why do we use the old school read and write that provide none of those features that are somewhat dangerous to use? Well, for one part, if you know what you're doing, then they are very fast. So there's no additional hidden overhead from all of the internal hidden variables that the standard I/O library uses. There's no hidden system calls behind our read and write calls that would slow us down. So there's no hidden system calls that are being used by the standard I/O functions, which may also cause our code to become non-reentrant. It's kind of a complicated topic, but reentrancy basically means, can we stop our code at any point and move out to another block of code and then re-enter our code without breaking things? And for the most part, the standard I/O functions are not reentrant, so they're not that means that they're not thread safe. That means that using things like signal handlers, you can't use printf when you're using signal handlers, things like that. We'll talk more about that as we get closer to block 3. And read and write are great for controlling exactly what is being written and read. You don't have to worry about those bufferings, and it happens when you tell it to, because there's no buffer. So some of the functions that are classics here would be things like, close down a stream, check if an end of file character has been reached, get the next character from a string, get our position, open things up, print formatted data out to a stream instead of to the screen. We can write single characters, read blocks of data. We can reposition a stream's position indicator. So the standard I/O version of lseek is fseek. And we'll talk about the difference here coming up in a couple of slides here between streams and files. We can get the next characters from standard in and just get the next character in general. So a bunch of great functions here. Some of the other standard I/O functions are getting strings from standard in, printing things out, writing characters, deleting things. We can print formatted data to a string, which is really handy. We can build up a string that we want to then use in another part of our code. Scanf is a great way to read formatted data back from standard in. So somebody typing at the keyboard, we can take a bunch of text that they enter and slot it into a bunch of different variables. And we can push characters back into streams if it turns out we don't want them. We can unget a particular character, and that only works because things are buffered. So files are streams. So standard in, standard out, and standard error, they're actually what are called file streams, not just file system files. So a file stream is something that wraps around and adds all that buffering to the underlying file descriptor among some other features. So the standard I/O library streams, they get connected with fopen to variables of type file asterisk. So these are pointers to capital files. That's the type of these things. And here's a sample code here where I'm saying, okay, I'm going to declare my file stream to be named my file. I'll use fopen to open it. I pass in the name of the file that I want to open, and I pass in the permissions bit that I want to open it up with. Streams get closed when the process terminates. So that's just like when we use a raw file descriptor, the streams get closed as well. So the raw file descriptors with open files, however, get passed on to child processes. And that's going to mean more to us once we get to block 3. But basically, when a process like your shell spawns a new child process with fork, which is the spawn me a new process function in C, then all the open files, all those open file descriptors get shared between the parent and the child process. So if the parent is working on a file and it spawns off a copy of itself, then that new child process can access the same file because the file descriptors are shared between the two. And the child and the parent can then close their own file descriptors down, and the other one will still retain access. Pretty interesting. All right, so let's talk about getting input from the user. So this is our last big example for this particular lecture here. So our header libraries get set up here, and then we're going to define some variables. We're going to use the number of characters that are entered, and we're going to set that equal to -5. Okay, so number of characters entered, we're going to be asking the user for a bunch of different characters so that we can demonstrate reading in input from the user. We are going to say, what is our current character? And again, we'll use -5. That's going to track where we are when we're trying to print out the characters. So this -5 value that I have here is a specific one that I've picked. It doesn't mean anything, but it's an interesting way for me to be able to tell, are these variables uninitialized, or have they never been moved from their initial setting? So an uninitialized variable can have any value. You have no idea what it is. Whereas something that I'm explicitly initialized here, if I later see a -5 appear, I'll know that I made a mistake and I never actually set that variable in the first place. So kind of interesting. And we're going to track the buffer size once we allocate it, and we're going to track line entered, which is going to hold the actual data that we get from the user. All right, so some interesting settings there. We're setting those to 0 and null. So let's see how they work. First of all, we have an infinite loop here. So while one is a way to say run forever. And the way this particular one is going to work is it's going to get input from the user by saying, first the user enter in a line of text and tell them they can exit with Control-C. So that is how they're going to exit out of this particular program. So printf, enter in a line of text. Then, this is some magic line here. GetLine is my favorite way to get text from the user. And you pass in 3 different parameters. And the first one is going to be the address to the array or to the string where the data should be placed. Buffer size is going to be the size of the buffer that you want to have opened up. And then you're going to say, where am I going to get the data from? So the 3 settings that we have here are special. By passing in standard in, we're saying, get this from the user directly. Ask the user for it, get character data from the keyboard. But when we send in line entered being equal to null and buffer size being equal to 0, this magic setting makes it so that getLine will automatically use malloc, and it will allocate a buffer for us dynamically on the heap to give us data, to give us a place to put the data that works for whatever amount of data the user types in. That's really handy. So if we don't know how much data the user is going to type in, we can use these settings to control that. We can actually, we don't have to actually say how big our buffer is. We just say, you go ahead and generate it, C, manage it yourself. Then we'll print it back out so that we can show the user what happened. So I allocated ZU bytes. So ZU is the way that you reference bytes, this buffer size variable, when buffer size is a size T, which is kind of that special type that's being used to track the number of bytes created. and then we'll also pass in the number of characters that were created for it. That was something we initially set at -5, and that will be created by the getLine function as the value that's returned. And then we'll tell the user, here is the raw entered line. So report back to the user what was entered. Okay, so then we print out the contents of that string. And this is a really handy technique. There's going to be lots of times in programs, especially 3 and 4, as you manipulate and push data back and forth, where you're going to need to ask your program, what actually is in that array? What's actually in that string? Because sometimes when you ask it to print it out, new lines and tabs and spaces, they all kind of disappear because they're all blank white space characters. It's hard to actually see their values. So here is a trick and a technique for displaying the contents of a buffer. So we're going to say, here are the contents of the entire buffer. So then we're going to print out some headers for the columns that are about to appear. And then we're going to run this particular line in a for loop. So we're going to go from the current character, so set it to 0, run this all the way up to the buffer size. So do this for every character in the buffer that was created for the user. Then on the next line we're going to say printf, and we're going to pass in 3 different variables formatted in different ways. So the first one is going to be a 3-position decimal character, which is going to be the current character. So that's going to go 0, 1, 2, 3, 4. That's just the which index into the array that we're examining. The second one is the line that was entered by the user, get the whichever current character we're at, and return that as a character, %C. Our last one is, again, a 3-position decimal value, but here we're passing in the same character. Well, you can take a character and convert it into its ASCII integer equivalent by casting that character as an integer. Really handy trick. And then we have to free the line entered string because it was created by malloc, which is on the heap. And if we don't free this up here, then we get a memory leak. Now, when the program terminates, all the array and the heap, or the stack and the heap and all the rest of the memory in virtual memory is all deallocated for us. But if this was a long-term running, if this was a long-running program, for example, we've got while run forever here, then we may eventually, these leaks might build up until we run out of memory on the system. So a good habit to free the memory when we're using it. And a note that when you use these special the special entries into getLine, getLine uses malloc and has to be cleaned up by itself. So here's the run of our program. So here's our compilation step at the top. We're going to call this thing user input, and then run it. And it asks, first of all, enter in a line of text, and tells the user to Control-C to exit. We then enter ABC space. This is a lowercase 0, or a lowercase o, a 0, an uppercase O, and I think this is an L, a capital I, and a 1. So a bunch of things that look very similar that are kind of hard to track. Let's enter them in and see if we can get some visibility into what those are with the code we have below. So then it says, allocated 120 bytes for the 11 characters you just entered. So remember, it's going to create a buffer for us. It's going to create on the heap memory for us. And in this case, even though we entered 11, it did 120. It's up to the operating system, it's up to the standard I/O for library for how many bytes it creates. And in this case, it went for 120. So then it tells us, here is the raw entered line. Here's all the characters we entered. And note there's that interesting new line that happened there. Then here are the contents of the entire buffer. Here's our headers. So then we can see here's the ABC, and here is the ASCII number, the ASCII code for those characters, 97, 98, 99. Here's the space. That can be hard to see. That's character 32. Lowercase o, 0, and capital O are all easily distinguished by their ASCII integer representation, and so are L, I, and 1 as 108, 73, and 49 respectively. Now here is a new line. Position 10 in this particular array contains a new line, and you can see that it messes up the formatting here, and it would be hard to tell what this thing was and why this got all messed up if it wasn't for the fact that 10 right here is the ASCII value, the integer ASCII value for that character. So we know that 10's a new line, and here's the proof. That's not just a formatting error, that's a new line character. Then we've got some things that look empty, and we look at the integer value for those, and those are zeros, which are null terminators, which makes sense. The way that buffer was allocated, apparently everything else got got null terminated, which is good. And we cut it all out because this is a long thing. It's going to do all 120 bytes, and we can see it all. And then we are able to kill off the whole thing with Control-C. All right. So what we could do, if we didn't want to see all the rest of these bytes, then we could just throw a null terminator in there, right? After calling our get line, we could say, kill this thing off. I'm just going to add a null terminator in there so that we don't see the new line. And the new line was added when I hit enter when I used the getLine function. If you don't want getLine to add that new line character in there, then just reset that last thing with a null terminator to erase the new line. All right. So one of our final little topics here is you can use the stat function on raw file descriptors and fstat on file streams to retrieve interesting information about the files and about directories also. You can tell what device it's stored on, so flash drives versus hard drives. We can tell the permissions and ownership for that particular file. We can tell the number of hard links that are pointing at it. We can tell the size of it, and perhaps maybe more importantly, we can tell when it was last modified and when it was last accessed. This can be really handy to help us get a sense for if we have a set of folders or files that have all been created. We can tell which one was created, say, most recently. We can take a look at the timestamps that are returned by stat. Stat returns an array, stat returns a struct of information when you call it on a file, and then you can just examine the various members of that struct to learn all this information about it. We could even tell stuff like the ideal block size for input and output. All right, well, I hope that was helpful in terms of learning more about file access with C. We will see you at the next lecture. Thanks.